So now we are going to see about factors affecting Dbtt curves. First of all, Dbtt curves. The ductile to brittle transition temperature is referred as Dbtt. It is defined as the temperature below at which a material changes from ductile to brittle behavior. This usually occurs at lower temperatures. It is mainly observed in BCC metals rather than FCC and HCP. For example, in ferrite steels. The different factors that influences on Dbtt curves are the effect of crystal structure, presence of grain size, effect of heat treatment, the presence of interstitial atom, specimen orientation, specimen thickness, and the presence of impurities and inclusion. This first, the effect of crystal structure. As we seen in the beginning, that the Dbtt curves are usually mainly observed in BCC metals. This is because BCC metals have limited slip systems at lower temperature. So at lower temperatures, dislocation cannot move easily. So because of this, fracture occur in a brittle manner. Rather, in FCC metals have more slip systems, so dislocation move easily. As a result, they usually do not exhibit a sharp Dbtt. We can see in the graph that for BCC metals that the graph show a steep rise, rather for FCC and HCP metals have almost flat curves. So this, as a result, BCC metals have Dbtt curve. And next, the effect of grain size. Grain size also strongly affects Dbtt. Fine grains make a metal together because they usually have many grain boundaries, so this helps to stop cracks. So the material shows a lower Dbtt. But in coarse grains make cracks spread more easily, causing a higher Dbtt. This is because in coarse grains the presence of grain boundaries are very less, so that the cracks can spread more easily rather than in fine grains. So presence of small grains, the Dbtt value is low, but in larger grains higher Dbtt value is seen. And next, the effect of heat treatment processes. Heat treatment processes changes the structure of the metal and affect its Dbtt value. Some heat treatment processes like normalizing and tampering make fine grains and lower Dbtt. Before we see the presence of smaller grains results in lower Dbtt. So normalizing and tampering will produce fine grains, so it results in lower Dbtt. But bad treatments like quenching without tampering makes the metal brittle and raise the Dbtt value. Next, the effect of interstitial atoms. Interstitial atoms like carbon, nitrogen, oxygen, and some more like manganese block the dislocation movement. This makes the metal harder but also less able to deform plastically. So as a result of presence of these interstitial atoms, the material becomes brittle at higher temperature than normal. Therefore, more interstitial atoms increases the Dbtt value. As we can conclude that the presence of interstitial atoms makes dislocation movement, blocks the dislocation movement. So this makes the metal harder and increases the Dbtt values. So next, the effect of specimen thickness. Thicker specimens create higher triaxial stress during loading, which makes it harder for the metal to deform plastically. As the thicker specimens, the triaxial stress during loading makes the metal to deform plastically, so that the cracks start grow more easily, causing higher Dbtt in thick specimens. But in thin specimens experience more plane stress conditions, allowing more plastic deformation. So thicker specimens have higher Dbtt, while thinner specimens have lower Dbtt. We can see in the graph which represents the thin specimens have lower DBDT while the thick specimens have higher DBDT values. This is because the thicker specimens may deform plastically while thin specimens allowing more plastical deformation. And next, the effect of orientation of the specimen. Specimen orientation changes how easily a crack can move through the metal. If the specimen is cut along the rolling direction, cracks travel more easily so that the DBT becomes higher. If it is cut across the rolling direction, cracks are blocked more, so DBT becomes lower. We can explain that in the rolling direction, if the cut is made along the rolling directions, the cracks can travel more easily so that DBT becomes higher. If, if, if the cut is made across the rolling direction, the cracks cannot invade, it is blocked so that DBT becomes lower. So DBT depends on whether the specimen is tested along or across the grain flow. We can see that the graph, the longitudinal orientation shows a steep rise, whether the transfers show lower DBT values. So the orientation influences more on the DBT values. Next, the effect of impurities and inclusions. Non-metallic inclusions like sulfides, oxides, nitrites act as crack initiation sites. We can see in the graph that the presence of inclusions have higher DBT values, while lower impurities show lower DBT values. So we can say that higher the inclusion value, higher the DBT value, while clean steels show lower clean steels which have lower impurities have lower DBT values. We see that the cleaner metal having lower inclusion value, having DBT lower than the metals which have more impurities than the cleaner metal. Okay, thank you.